Right, so this is a short chapter on Ramsey theory, just for graphs. Ramsey theory is a discipline in its own right. I've written just a little bit about that in the blurb for the Ramsey chapter in the book. I'm not going to repeat that here, but we'll just be dealing with graphs. And let me take as the starting point Turán's theorem, which said that if a graph is large enough in the sense of having lots and lots of edges on some fixed number of vertices, then it must contain something. Something could be anything we wish for example, a complete graph of given size kr, right? So Turán's theorem told us that on some fixed number n of vertices, if this graph has enough edges, then it will contain a kr subgraph. Now, what happens if we assume not that the graph has lots of edges, but that it has lots of vertices? Can we then deduce something similar, like then it must contain this or that? And of course, the answer is trivially no, if this or that just means one thing. So a graph just on the strength of having many vertices will not contain anything interesting that we can choose in advance. But it might happen that a graph contains one of two things that we specify in advance. And that is exactly Ramsey's theorem in its simplest form. So it's simple. There'll be a more elaborate version later. And finite, I'll give you an infinite version as well. And that says that for every size r of a subgraph we wish for, or order r, for every r, there's an n such that for every g, if g has enough vertices, at least n vertices, then it contains kr as a subgraph, or it contains the complement of kr as an induced subgraph. Which is just a glorified way of saying that it has at least r independent vertices. It has a set of vertices of size at least r that's independent, right? So if a graph is just large enough, given r, just make it large enough, then you can be sure that it has r vertices that are pairwise adjacent, or it has some r vertices that are pairwise non-adjacent. That's Ramsey's theorem. So if you next have your granny visiting and she complains that your flat is not tidy enough, just tell her that you proved in this theorem, in this lecture course, that complete disorder is impossible. Right? So that's the way of rephrasing that theorem. Complete disorder is impossible. If you just have enough of a mess, then in that mess, you will find any amount of very, very nicely ordered structure that you specify in advance. But make enough mess and you'll be all right. Okay. So that's Ramsey's theorem in its simplest form. And now, going back to Turán's theorem, it may come as a bit of a surprise that sort of roughly half the edges seem to be enough to give us a kr subgraph. So either our large enough graph G contains a kr, or its complement contains a kr, So G itself, or the complement, cannot be expected to have more than roughly half the number of possible edges, half of all possible edges, right? So how can it be possible that having only half the possible maximum number of edges is enough to force a KR? Right? Remember, Turán's theorem told us that we needed something like R minus 2 over R minus 1 proportion of the possible edges. And I mean, R minus 2 over R minus 1 is something like 9/10ths, right? Like 90%. 9/10ths sounds more impressive than R over 2 over R minus 2 over R minus 1. And 90% sounds even more impressive than 9/10ths. So we really, really need a lot of the edges. And R, of course, might be 100 rather than 11. A lot of the edges to force a KR. So how is it possible that seemingly here half the edges will do? And the answer is that in Ramsey's theorem, first of all, it only works for large enough graphs, whereas Turán's theorem works for all graphs. But that's not the important point here. The important point is that we keep our options open. So we're just wishing for either this or that, not making up our minds in advance whether we want a KR in the graph or in the complement. If we do insist that we have a KR in the graph, we need that many edges, even if n is large. And if we insist on having it in the complement, we need that many non-edges. So keeping our options open as to which of these two events is the outcome that the graph is kind enough to offer to us, that helps in reducing drastically the number of edges needed to about half of the possible edges. And if you look at what happens in Turán's theorem, if you just miss this threshold, right, if you have lots and lots and lots of edges, but just not enough to force a KR, then you do get rather more than a KR in the complement. Right? What you get is R minus 1 sets that are huge. How big are they? They're something like n divided by R. Right? By R minus 1 rounded down. So these are, think of n as big. This is much, much, much bigger. So if we don't have a KR, and the graph is really large, n is really big, then in this range of numbers of edges that are just below the Turán number, we get a structure like that, and rather than just getting a KR in the complement, we get much, much bigger complete graphs in the complement. So the two are simply different questions. They don't contradict each other in any serious way. Right, okay, so let me rephrase this in a more colorful way. And that is for every R there's an n, such that for every true coloring of the edges of Kn, and by true coloring, obviously, I don't mean a proper true coloring, just not in the sense of the coloring chapter that adjacent edges need to be differently colored. Just any assignment of either red or green to every edge. For every true coloring of the edges of Kn, there exists a monochromatic KR in this KN. And what's a monochromatic KR? Well, what the name suggests. It's R vertices in RKN with its edge coloring, all whose edges have the same color. Right, and that's clearly the same as here. If you have this, just use green for edges of G and red for non-edges of G, and then you get that, and conversely as well. So that's the more colorful way of phrasing the simple finite version of Ramsey's theorem. Let me prove that. In a way that is easier to prove, and that is for infinite graphs. What does it say for infinite graphs? It says that for every true coloring of the edges of K aleph naught, there's a monochromatic let me say okay. For every true coloring of the edges of some K aleph naught, which I call K, there's a monochromatic subgraph of that K, and that is also that is induced. So right. That's the infinite version, and here's a proof. It's very simple. Here's our infinite complete graph, say, on the natural numbers as the vertex set. We pick any vertex, could be 0, could be anything. And look at the incident edges. So this has lots of edges going out. Some of them are red, some of them are green. One of these two neighborhoods has got to be infinite. There's infinitely many neighbors, all of them. All the other vertices are neighbors. So the edges there are colored with true colors. One of these must be infinite. Say green is infinite. Okay, then we continue inside this green neighborhood of this first vertex, and we remember that we do that by encircling that with green. Okay, so here we do the same thing. We pick one of these vertices and look at all its neighbors. And some of these neighbors are green, and some of them are red. So more precisely, the edges to some of those neighbors are green, the edges to some other neighbors are red. And let's continue in one of those two sets that is infinite. At least one of them will have to be infinite, because two finite sets can't have union an infinite set. So one of them is infinite. Say this one is infinite. And then we encircle this vertex red. And we keep going. Ad infinitum until we've got through all our vertices. Right, we make sure that we go through, well, don't even have to, just need infinitely many. Right, and then we look at the circles that we put around our chosen vertices. We chose infinitely many of these vertices, and each of them has a green circle or a red circle around it. And so one of these must occur infinitely often. And say if green occurred infinitely often, then I claim that these chosen green vertices form a green infinite complete subgraph of our edge-colored infinite complete graph. And why is that? Well, because after putting we put the green circle around this vertex because everything we did from that point onwards, all the vertices we considered after that were adjacent to this particular vertex by a green edge. We disregarded all the others. And similarly for this, we only considered from here onwards vertices to which this vertex sent a green edge. So when we look at our infinite sequence of green encircled vertices, the later ones are in this special set of every earlier one, because we only looked in that set of green neighbors. So in particular, the edge between those two is going to be green. So all the edges are going to be green. And that's the proof. All right, questions? No. Right, then can we imitate this proof for the finite theorem? So what do we want now? We want R encircled vertices. And we want to play the game inside some kn rather than k infinity. So this n has to be large enough that we don't run out of steam. How many steps do we need? How often do we need to do this? How many iterations do we need? Well, the worst thing that can happen is that these half of the circles are green and the other half are red. So if we want a kr, we need something like 2r iteration steps. Then we have 2r vertices with a circle around them, then at least r of them have the same color in the circle. Okay, so we want 2r steps. How large does n have to be to allow us to take 2r steps without running out of vertices? So the algorithm will be, we continue in the bigger half. Right? Neither of the halves is going to be infinite. We continue in the bigger half. So at every step, we divide the neighborhood in two sets. And the bigger half has size at least half that. Right? So we retain at least half the vertices that we had previously at each step, well, minus 1. Okay, so very roughly, we need 2r steps, and at each step we halve the number of vertices that we're playing with. So if we start with 2 to the 2r vertices to begin with, then we can do this halving 2r steps 2r times, and we're not going to run out of vertices yet. So that's roughly the finite proof. It's also very, very easy to deduce the finite theorem from the infinite theorem, and I'll show you that in a moment. Okay, before I do that, let me give you the infinite general version. Maybe I'll put that on the top board still. Okay, Ramsey, general, finite. Now we want to color not just with two colors, but with some finite number of colors. That finite number is going to be C, so for every C, and we're going to color not just the edges, but the K subsets of our vertex set. So for every C and for every K, and then we give ourselves a target size of a monochromatic set R, then there exists an N such that for every set X with at least n elements, or maybe I'll just give it a name. No, let's do that. For every set with at least n elements, or for every C coloring of the K subsets of X. Right, that's my notation for the K subsets, the subsets of size K of the set X. There is a monochromatic Z in X with at least R elements. And what is that? What's a monochromatic Z? Well, it's a subset of X. So here we have our big set X, and then there's Z in there, and we colored all the K sets of X, right? So these are the K subsets of X. They got colors. Every K subset got a color, and Z is going to be monochromatic if all its K subsets have the same color. Right? So it's slightly misleading because monochromatic sounds as though Z has a color. Z doesn't have a color. Z is a subset of X, so think of it as a set of vertices, and the edges on it, or the K-sets on it, have colors. Still we call Z monochromatic. Okay, so that's the general finite theorem, and well, while I'm at it, I may as well give you the infinite version as well. Infinite, so for every C and K, and every, so we don't need R, we don't need N, and for every C coloring of the K subsets of the natural numbers, there is an infinite monochromatic subset of the natural numbers. Right, so that's an infinite set of points, all whose K-sets have the same color in this given coloring. Okay, so let me prove the infinite version. And we do induction on K. K is the size of the sets that get a color. And of course, we could start with K equals 2 and use the theorem we just proved up there. But for good measure, let's include the proof of the theorem up there and start with K equals 1. So we'll be proving that as well in the first induction step. So what happens to K equals 1? Then we have the natural numbers, and we assign a color, one of C many colors. C is some constant number, one of C many colors to the one subset of the natural numbers. So every number gets a color. Only finite many colors. So by inverse pigeonhole or something, one of these sets must be infinite. And that infinite subset of the natural numbers, all whose elements as one subset's got the same color, is our Z. Yeah, so start at K equals 1 is easy. So let's do the induction step. We do pretty much the same thing. We follow the same idea as in that proof. Now we want to use induction. So we pick a vertex and look. So consider some number k, and we're assuming the theorem for k minus 1, or smaller values of k. Let me equip myself with some colors here. And now we use the induction hypothesis on all these vertices. Right? Everything except that one vertex. And here, we color the k minus 1 subsets. How do we color them? Well, every k minus 1 subset here forms a k set together with this one special vertex. That k set got a color. We have a coloring, a fixed coloring of all the k sets. So we use that color of this k set to color this k minus 1 set. Okay? Well, then there's an infinite subset up here that is monochromatic. That's our first Z that the induction hypothesis gives us. There's an infinite monochromatic subset with respect to this k minus 1 with respect to this C coloring of the K-1 subsets of this set. So suppose all these are green. Right. That means that together with this vertex, they are colored green in the C coloring of the K sets, by definition of this C coloring of the K-1 sets. So if this happens, then we put a green circle around this vertex. And then we continue as before. So we pick a vertex here, and then we color the K-1 subsets of everything except these two vertices here. And how do we color them? Well, in the same way. These K-1 subsets here form K sets together with this special vertex in the given coloring. So there's an infinite monochromatic subset of these K-1 subsets here. And of course, that means that, together with this vertex, they had that color in the given C coloring of the K sets, and we put a circle with that color around this vertex. And continue. We always continue inside this infinite monochromatic subset that we found at the previous step. Right, we're really zooming into that infinite set of integers, taking an infinite subset, another infinite subset, another infinite subset, discarding many, 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 many other vertices, or points, elements, numbers. So we do that infinitely often, and we never run out of steam because we can take infinite subsets infinitely often. So at the end of the day, we get a sequence of chosen points, and these chosen points, these chosen elements, all have circles around them, but we only have finitely many colors that we used to encircle these points. So one of these occurs infinitely often. And that sequence forms our infinite monochromatic set Z. If they all have circles green, that means that each one of them forms a green K-set together with every K-1 set of vertices we even considered after it. In particular, those others that were chosen to selected for Z. Yeah, done. Questions? It's nice and simple. Okay, so let me deduce the finite general theorem from the infinite one. Right, the finite general one says here, for any number of colors, for any size of subsets that we are targeting, and for any size of the target set that we want to achieve, there's an n such that every set, if it's bigger than n, so every large enough set, no matter how we color it with C color, how we color its K subset with C colors, has a monochromatic subset of size at least R. Yeah, I forgot the for every R. Right? Okay, so if that fails, what does that mean? If this fails, then let's just do this mechanically. We flip all the quantifiers, so then there exists C, K, R, such that for all n, there exists a bad C coloring of the K subsets of little n. So little n is the set of the natural numbers before it. That's just jargon in set theory. Or, if you want to be pompous, that's the definition of little n. All right? Is that clear? So, if general finite Ramsey is false, then it's not true that for every C, K, and R there is an n such that blah, but rather there exists bad C, K, R such that every n set, no matter how large, has a bad C coloring, where bad means that there's no monochromatic Z in n of size at least R. Right? Every n, it's possible to color the K subsets of n, no matter how large n is, with C colors, so that there's no R set in n with which, with respect to this coloring, is monochromatic. Okay. So let me give you a visual start of the proof and then ask you what I have in mind. So we're going to use the Infinity Lemma. And what is Vn? That's the bad colorings, the set of all bad C colorings of the K subsets of n, right? We're assuming that such a thing exists. There exists a bad C coloring of the K subsets of n, for every n. So these sets Vn are not empty. That's the whole point. Well, one of the whole points. They're non-empty. And every bad coloring of the K subsets of n induces a bad coloring of the K subsets of n minus 1, because n minus 1 is a subset of n, right? So its K subsets are necessarily colored when we color the K subsets of a bigger set. So a bad coloring of, or any coloring of the K sets of n induces a coloring of the K sets of n minus 1, and if this is bad, then that is bad too, because if it wasn't, then that'd be an R set in n minus 1 that's monochromatic with respect to this coloring, but then that's an R set of n as well, And that's still monochromatic in this coloring because that's the same coloring on n-1. Okay, so we have this set up. So by the infinity lemma, there's a ray through this system. And we use that to define a bad coloring on the case subsets of the entire set of integers. And how do we do that? Well, take any case subset of the natural numbers. This case subset will be contained in some n. In that n, this case subset got a color because we have coming from the yellow dot in Vn. We could also have chosen a later yellow dot because these later these later m's also contain our case subset because that was already contained in n, and here it would also have received a color, but that coloring induces this coloring, and therefore it's the same color. So that's well defined. Once more, I'm defining, let me write this down, by the infinity lemma there's a ray in this graph which defines a C coloring of the case subsets of the positive integers of the natural numbers. This is a bad coloring. There isn't even an R set in the natural numbers. That is monochromatic. Why is that? Well, if there was an R set, then this R set, R is given, right? That R set would be contained in some n, some little n. In that little n, the case subsets of that R set already got a color, namely the eventual color of this. But that coloring of the case subsets of this R set is not monochromatic. That doesn't make the subset Z monochromatic, because in that case, this would be a good coloring of the case subsets of N, which it isn't by being yellow. So there's no monochromatic Z even of size R, let alone an infinite one. Okay. So if you can do applications of the infinity lemma by autopilot, which you probably can already, certainly if you've done some exercises, it's always the same idea. Then that would seem completely obvious right from the start, where this done for finite is a little more cumbersome than doing this for finite, because here we had to work out what n to start with. Right? We had to start the proof with saying, let n have size at least, I don't know, 2 to the 2r. And then worked through it, and then found, surprise, surprise, that after 2r steps, we've still got a point, a vertex. And here you have to work out how large to choose the n so that it all works. Of course, it's the same kind of computation, but you have to count the number of, it's more complicated. So this is very, very simple, but of course it doesn't give you anything quantitative, it just gives you the qualitative theorem. Questions?